Good morning, one and all. So, let us start with the lecture number 52 in control systems. So far we have started the module number 5. It is about state variable analysis. And in state variable analysis, we have seen some 3, 4 different numerical, that is, how to prepare the model of state variable. And there are many such examples. I will keep on doing it, and with that, as the syllabus demands, there are certain uh, more techniques that we are supposed to learn in the state variable analysis. So one of the very important part is the solution of state variable analysis. So whatever abcd matrix we are generating, what for they are used. So you have seen there is x dot is equal to axt plus but. So in this case, xt is the state variable, x dot t is the differential of state variable, and ut is the input. A matrix is state matrix and b matrix is called as input matrix. From here, if it is there are two variables in case of this above defined state variable model. And if I say that xt is actually, there are two state variables, so in that case a matrix will be 2 cross 2, that is total number of state variables and a square matrix of that dimension. And b matrix in that case will be 2 cross 1. Ut will be only ut, so ut is the input. And x dot t also will be x1 dot t and x2 dot t. Now in this case, if I ask you find the system solution, what is meant by solution? So what we find here, so that is our next topic actually. So x dot t, we find that x1 dot t is equal to something of xt plus something of ut, and x2 dot t is equal to something of x1t plus something of x2t plus something of ut. So we are actually having two equations, but those two equations we are having in matrix form. Now you have done solution of differential equation in first year or second year. So in this case, actually we are supposed to find out the solution of this differential equation. Now what is meant by solution of differential equation? If you go in case of RLC circuit, so let us understand it from a practical point of view, what is meant by solution of a differential equation. So in this case, we are going to write in the left side IL dot T or I dot T and VC dot T. That means we are actually representing the equation of RLC circuit current, which is a function of time, as well as RLC circuit capacitive voltage. Okay, so we are writing the equation of rate of change of those things. That means left side is x dot t, I dot t. I dot t means actually dit dt. So with respect to time, how the it is changing, that equation we are writing. And in the right side, that will be in terms of something of it plus something of vct plus something of ut. So I dot t will be a function of it, vct and ut. Similarly, vc dot t also will be a function of it, vct and ut. Now from there, I will ask you find the solution of that state variable model. So what is meant by solution? Solution is means from I dot t is equal to something of it plus something of vct plus something of ut. You have to tell me what is the actual equation of it. And second state variable vc dot t, you have to tell me what is the equation of vct. So that will be our next part. And while finding the solution, first step is finding the state transition matrix. So there is a time matrix, what is called a state transition matrix, which actually evolves with respect to time. So in this case, first thing today what we are going to do, so we are having three numericals today and the properties of stm. So don't write stm, write state transition matrix only in the exam. And finding the state transition matrix is a big task, and student gets scared because they don't understand it, and that's why they are not able to find it. But numericals are very repetitive and there is no difficult steps or nothing. Only you have to do a partial fraction and you have to take inverse Laplace transform. So today's topic, what we are going to see is what is a state transition matrix. And what is the significance of state transition matrix? You have to say that the state transition matrix is required just to find out the solution of state variable analysis. So all these models and all these things we are doing, if we are not able to use this model for finding the actual system parameter or for actual system variable, defining that, actually the state transition matrix is used. So in exam, they can ask you directly that find state transition matrix for 5 to 8 marks, or they can ask you find the solution of given state variable. So abcd all matrix should be given and you are supposed to find out the solution of that matrix. So in that case, you don't actually require c and d matrix. For finding the solution of state variable, you require only a and b matrix. And finding the system transfer function, you require ABCD matrix, all these four. So if I give you only A and B matrix, in that case, you can find out what is the system solution. And again, I am telling you repeatedly what is meant by system solution. So in this case, RLC series circuit, always remember. So we have defined this x dot t is equal to axt plus but. Left side it is I dot t and vc dot t. Right side it is all the parameters of it and vct and ut. That is the input. So what is meant by solution? Whenever from I dot t and equation, we are finding a equation of it. Equation of it not in terms of it or vct or ut. Equation of it like this: 2 e raised to minus 3t plus 7 e raised to minus 5t. Likewise, so it's a mathematical equation. It's not a equation given by variable. Okay, so whenever we will be doing the solution, at that time be careful what kind of equation we are finding. And in lab also, for this experiment number 9, whatever we will be doing, there also you have to find the solution of state variable equation. Now in this case there will be two solutions. Okay, so today only we can see what is the solution of homogeneous state variable model. Now in this case, x dot t is equal to axt plus but. This is called as a non-homogeneous system. Why it is non-homogeneous? Because the external forcing function is given. Now you have done this homogeneous system solution, non-homogeneous system solution, or homogeneous and non-homogeneous differential equation solution in your first year and second year in ordinary differential equation, but you did not know what is exactly the meaning of that. Okay, so in case of homogeneous, you have to remember, in case of homogeneous system, this but part will not be there. In that case, x dot t will be a into xt. So what is this ut? Ut is called as a forcing function. Okay, so in signals and systems also, you might have seen that any system is having two responses. In response of any system, there are two parts. One is called as zero input response, another is called as zero state response. What is meant by zero input response? This zero input response actually is a response provided by the initial condition. So whenever there is a capacitor, suppose capacitor is storing some initial zero point 0.5 volt in it. Now you are giving some external 10 volt supply to the capacitor, 10 volt DC. Now this 0.5 volt will be there, and on top of that, the capacitor will try to charge up to 10 volt. Okay, so this initial whatever is the condition, that thing actually is responsible for the transient behavior of the system, and that is actually called a zero input response. So there are very important things I'm telling. First thing is what is meant by homogeneous system. So in homogeneous system, this but part is not there. In homogeneous system, it is only x dot t is equal to axt. Okay, that means differential of state variable is equal to state matrix and state variables. That's all. There is no external input or forcing function or external function or source function connected to the system. In that case, it is called as a homogeneous system equation. So we have to find out the solution for that. And next step is x dot t is equal to axt plus but. We are connecting some external input to the system, and we are trying to find out the system response or state variable equation with respect to the external input connected to it. And whatever system response we find from there, it is called as a non-homogeneous system solution. So today we will see what is meant by homogeneous system solution, and there this but part will not be there. So for finding homogeneous system solution, first what we have to do is we have to find what is the state transition matrix, and with that we have to multiply the initial condition. Okay, so this thing is called as xt. Xt is nothing but x1t, x2t. In that case, it will be given as x1 0 and x2 0. So this matrix will be called as x0, and this matrix will be called as x1 0 and x2 0. That is the initial condition of two two variables x1 and x2. Suppose x1 is an inductive current, so maybe this x1t value will be x10 value will be maybe 0.2, and x2t may be the capacitive voltage, so that value may be 0.7. So in that case, x0 matrix will be 0.5, 0.7. Okay, so that matrix, if you multiply with state transition matrix, you get the solution of homogeneous state variable system. So all these things we are going to see today, but before that, main important thing is how to find the state transition matrix. So let us have a look through in the state transition matrix, STM, and finding state transition matrix is the main job in finding the solution of either homogeneous or non-homogeneous system solution. So I have written some 5-6 pages. I will be posting this thing to you with this lecture link. Please go through And these two three numericals, if you do, so there is one numerical of two dimension A matrix, there are two numericals of three dimensional state matrix. So I think if you do these three numericals, you will understand all about state transition matrix. So there are two three questions generally from this state transition matrix asked in the exam. First thing is define state transition matrix and what are its properties. Okay, so it is generally asked for 5 marks, so I have mentioned it in the end of the second page. That is what are the different properties. So all the properties are equal to the exponential properties. So you can see from here state transition matrix is given by phi t in time domain. In Laplace domain it is called as phi s, and also in time domain phi t is called as e raised to at. So this a is nothing but a state matrix. So here e raised to at actually is a vector. Okay, and it's actually represented in terms of a matrix, it's not a scalar. Okay, so a is two dimensional matrix, 2 by 2. Likewise, whatever is given here, so this a is 0 1 minus 2 minus 3. So in case of a you have to substitute that, and accordingly you have to write what is the state transition matrix. So let us find out state transition matrix for some case, and let us see first what is state transition matrix. So where a is the state transition matrix e raised to at, where a is the state matrix, that is the most important matrix in state variable analysis. Given for the state variable representation, x dot t is equal to axt plus but, where a is equal to 0 1 minus 2 minus 3. You can see here, to find the solution of this system. Now first told you what is this system. This given system is actually a non-homogeneous system. Why non-homogeneous system? Because there is a external forcing function present here. And some system, this but part might not be there, x dot t is equal to axt, only it is there. That thing is called as a homogeneous system because forcing function is not given in that case. To find the solution of this system, that is this non-homogeneous system, means finding the time domain equation of state variables xt. That means you have to find the equation of x1t and x2t. That means that is the solution of the state variable x dot t is equal to axt plus but. So it is saying that what is meant by finding the solution. So this paragraph is telling you what is the meaning of finding solution of state variable model. So x dot t is equal to axt plus but, it's given. To find the solution of this system means actually finding the time domain equation of x1t and x2t. Okay, first step in finding the solution of given x dot t is the finding of e raised to at or phi t. So this is the first step. So if I am giving you that find the solution of the given non-homogeneous system for 10 marks, for finding state variable, for finding state transition matrix, I give 5 to 6 marks. Okay, so it is very important, that is e raised to at has to be found first. Without finding e raised to at, you cannot find the solution of state variable model. So first step in finding the solution of given x dot t, whatever is written here, is to finding the e raised to at or phi t. What is phi t? So here first I am writing what is phi s. Okay, so phi t in Laplace domain is called as phi s. That is nothing but si minus a inverse. Be very careful. Si minus a inverse, not only si minus a, but si minus a inverse. This is called as state transition matrix in Laplace domain. And how can you come back from phi s to phi t? I have to take the inverse Laplace transform. So finally phi t is equal to, that is state transition matrix which we are going to find shortly, is equal to inverse Laplace transform of si minus a inverse. Okay, so phi t is equal to inverse Laplace transform of si minus a inverse. So first you have to find si minus a, then you have to find si minus a inverse, and then you have to do partial fraction and all, and whatever you are getting there, find the inverse Laplace transform of that and come to phi t. So phi t is equal to inverse Laplace transform of si minus a inverse. E raised to at or phi t is called as a state transition matrix in time domain. Phi s is the state transition matrix in Laplace domain. Now, what is required for finding state transition matrix? Only A matrix is required to find e raised to at. Nothing else is required. B, C, D matrix, nothing else is required. Only A matrix is required. So in your exam, we can ask you for two-dimensional e raised to at or three-dimensional e raised to at. So if three-dimensional e raised to at is asked, it itself is a 8 to 10 mark question. And if two-dimensional e raised to at is asked, it is not a 10 mark question, but sometime something else may be asked with that. So here I have started with a two-dimensional A matrix. So given A matrix, so x dot t is equal to axt plus but. In that case, A matrix or state matrix is given as 0, 1, minus 2, minus 3. In that case, find what is the phi t. So this is the question, that is A matrix is given. A matrix is given as 0, 1, minus 2, minus 3. Now find what is called as a state transition matrix or STM or a phi t or e raised to at. So for finding phi t, first we have to find out phi s, that is state transition matrix in Laplace domain. And after that we take the inverse Laplace transform of phi s and we get phi t. So what is SI? I is the identity matrix. So 1001 multiply S with that. So S00S. Okay, so this is the SI. A is given. So what is SI minus A? So SI minus A is nothing but S minus 0, that is S. Then this 0 minus of 1, this is minus 1. Then this minus 2 will become plus 2. And this is S minus of minus 3, that is S plus 3. So actually what you are finding is SI minus A is S minus 1, 2 and S plus 3. Then phi s is equal to Si minus A inverse is equal to 1 upon delta. Now all those adjoint cofactor thing you do. So in doing it for second order system, what we do is we diagonally interchange the position. So this S plus 3 comes up, S goes below, and the another diagonal we change the sign. Okay, so the main diagonal we change the position, that is S plus 3 goes up and S comes down, and the other diagonal we just change the sign. So this minus 1 becomes 1 and plus 2 becomes minus 2. So this is actually phi s, which is 1 upon delta S plus 3 into S, 1 and minus 2. And what is delta? Delta you can find from either from this transposed thing or from the Si minus A main. You are finding it as S into S plus 3 plus 2. That is S square plus 3S plus 2. That is nothing but S plus 1 and S plus 2. And generally in exam also, whatever delta we design, so we actually design these problems and ask you, generally in exam whatever we ask you, this delta is factorizable. So as here also you will find S square plus 3S plus 2, this is factorizable into S plus 1 into S plus 2. Okay, and then you have to put it inside this matrix and you have to get partial fraction. So I think this page is clear. So finding phi t e raised to at. First step is find Si minus A. We have found it. Then find Si minus A inverse. And for that there are two steps. One is 1 upon delta. So delta can be found out by all this cross multiplication. You know how to find the determinant. Delta is nothing but the determinant. And then adjoint cofactor and all these things we do. And we find phi s equal to 1 by S square plus 3S plus 2. And it is like this. Next is finding that what is exactly the phi t. So in the previous page, we will see towards the top, we have found phi s partially. So e raised to at is actually the phi t inverse Laplace transform of Si minus A inverse. So this is actually now Si minus A inverse 1 by S square plus 3S plus 2, S plus 3, 1 minus 2S. I have written once again because in the previous page towards the end we had formulated it. Now what to do? Now take this denominator, whatever is the denominator delta inside the bracket. So it is S plus 3 divided by S plus 1 S plus 2, because S square plus 3 S plus 2 is nothing but the determinant. So S plus 3 divided by S plus 1 S plus 2, this is 1 by S plus 1 S plus 2 minus 2 by S plus 1 S plus 2 and S divided by S plus 1 S plus 2. And now next part is you do the partial fraction. So how to do partial fraction? I think you know it is very simple. The first order partial fraction, there is no even d dt and all those things you have to use here. So after doing partial fraction, what you can find is this is 2 by S plus 1 minus 1 by S plus 2. This thing is 1 by S plus 1 minus 1 by S plus 2. So after you find partial fraction, just check it once again whether you are getting the proper values of the function or not, because this is actually a very easy numerical. There is nothing difficult in that. Only Si minus A you have to do and take the partial fraction and take the inverse Laplace. So very easily actually you are getting the 8 to 10 marks. So every step you should check. So how to find whether this is 1 by S plus 1 S plus 2? So just check this. So multiply this. This is S plus 1 minus S minus 1. So S plus 2 here when it goes up, and it is minus S minus 1. That means S plus 1 minus S minus 1. That means 1. Here you check 2S plus 4 minus S minus 1. That means S plus 3. Likewise. Okay, so this is how to find out whether this partial fraction is correct or not. So steps are: first find Si minus A, then find Si minus A inverse. This denominator should be factorizable generally, but even if it is not factorizable, you should be able to proceed. But obviously, we should not be asking you imaginary poles and all those things here. Generally, it is not asked. If your bad luck is very bad, it might be asked, but generally in exam we be sensible and we ask you numerical where this denominator is factorizable and it is like this, and then take it inside and then do partial fraction and final step. So this is whatever you are finding inside the bracket. This is actually Si minus A inverse. Now last step is you have to find out inverse Laplace transform. So there are actually two inverses you have to do. First inverse is the Si minus A inverse, that is a matrix inversion, and second thing, a inverse Laplace transform. So 2 by s plus 1, what will it be? 2 e raised to minus t, minus 1 by s plus 2, it will be e raised to minus 2t. 1 by s plus 1 e raised to minus t, 1 by s plus 2 minus of e raised to minus 2t. 2 by s plus 2, this is 2 e raised to minus 2t. 2 by s plus 1, this is 2 e raised to minus t. 2 by s plus 2, 2 e raised to minus 2t, minus 1 by s plus 1, that is minus e raised to minus t, and ut. Why am I writing ut? Is here, the significance is it is a causal function. Okay, that means I'm trying to show that the phi t or state transition matrix is actually a causal function. So this is how you are supposed to find phi t, and finally you have to write phi t e raised to at. This is a state transition matrix. It helps in solution of state variable model. So let it be a homogeneous system, let it be a non-homogeneous system. For any solution of state variable, first you have to find what is the state transition matrix. And with this state transition matrix, if you multiply the x0, so dimension of x0 is again 2 cross 1. Okay, so just with this phi t, if you multiply x0, done. That is the solution of homogeneous system. So with this, just I give you a condition for x0. So it may be 0 into 1. Okay, so 0 into 1 is, sorry, 0, 1. Okay, in bracket, 2 rows, 1 column, 0, 1. So in that case, you'll be finding that just multiply phi t with x0, that is 0, 1, and you are getting what is called as the state transition matrix. Sorry, the system solution. I'm sorry, the system solution in for a homogeneous system. So we'll be doing one numerical today, that is find the solution of homogeneous system, and we will see how it is. Next is properties of state transition matrix. So this question is asked for 5 marks. So these are all properties of exponential. So what is the property? First property, what is e raised to at? And remember, always A is a generally 2 by 2, 3 by 3, 4 by 4 matrix, depends on number of state variable. If n is equal to 2, number of state variable is equal to 2, A is a 2 by 2 matrix. A is 3, in that case, e raised to at will be a 3 by 3 matrix likewise. So e raised to at is equal to I. Okay, so if A is 2 dimensional, 2 by 2, then I also will be 1 0 0 1. If A is 3 dimensional, then I will be 3 by 3, that is 1 0 0 0 1 0 0 0 1. Likewise, you have to change. So properties of state transition matrix, 6 properties I have told you in the exam. If it is asked for 5 marks, just write these properties. If it is asked for 10 marks, sometime it is possible. Then for every property, you have to do some numerical. Okay, so e raised to at is equal to I plus at plus 1 by 2 factorial square t square. It goes up to I is equal to 0 to infinity. So 1 by I factorial a raised to I t raised to I. So in this case, a square t square. What is the dimension of that? A is 2 by 2, a square is also 2 by 2. Okay, and t is nothing but whatever is the time. Just you have to multiply with a square. That means this matrix 1 by 2 factorial a square t square. This also will be a 2 by 2 matrix. So everything is a 2 by 2 matrix. One is one I is 1 0 0 1. At is whatever is the a matrix, multiply t with that. Okay, so t will be there. Now depending on every time instant, so I told you that at every time instant you have to find out what is the state, what is the value of that state variable. So this e raised to at helps you finding that. Okay, so all are 2 by 2 matrix. If you just add all these things, that is I at 1 by 2 factorial a square t square, 1 by 3 factorial a cube t cube, all those things if you are adding, all are 2-dimensional matrix. So you'll be finding e raised to at also will be a 2 by 2 matrix. And what will be the e raised to at? That we have shown you here. So if a matrix is 2 by 2, in that case e raised to at also will be 2 by 2. So that is the first property, that is e raised to at is matrix exponential. It converges for all a in the state matrix and for all finite time t. Okay, so t should be finite, t should be causal, and in that case we'll be able to find that e raised to at is converging. E raised to a into 0. So substitute t is equal to 0. If you substitute t is equal to 0, all this right part will become 0. So in that case, e raised to a into 0 is equal to I. Okay, so that you can prove from the top identity. E raised to at is equal to I plus at plus 1 by 2 factorial a square t square. So for time t is equal to 0, that means at the start of the experiment, okay, you will be finding e raised to at is equal to I. Okay, e raised to at plus tau. So there will be a convolution kind of a thing we'll be doing while finding the solution of non-homogeneous system. So in that case we have to use this identity e raised to a into t plus tau, that is e raised to at into e raised to a tau. So this also will be a 2 by 2 matrix. So e raised to at will be a 2 by 2 matrix, e raised to a tau. Okay, so this is actually the amount of shift that we cause in case of convolution, that is e raised to a tau. And if you're multiplying two 2 by 2 matrices, you'll be getting again a 2 by 2 matrix. So e raised to a t plus tau is equal to e raised to a t into e raised to a tau. Now e raised to a t inverse, e raised to a t inverse also will be e raised to minus of a t. If e raised to a t is two-dimensional matrix, e raised to minus of a t will be a two-dimensional matrix. D dt of e raised to a t, very important thing. Differentiation of state transition matrix is equal to a into e raised to a t or e raised to a t into a. This you can do and you can find out. So differentiation of state transition matrix, that means whatever thing you have found out here, okay, that is 2 e raised to minus t minus e raised to minus 2t and all, differentiation of d dt of phi t is equal to differentiation of this, and that will be is equal to a into e raised to minus t or e raised to minus t into a. Okay, so this is pre-multiplication, post-multiplication, all these things you should know in case of matrix. So either you pre-multiply e raised to at by a or you post-multiply e raised to at by a. Both the things will be same as long as e raised to at is a state transition matrix. So these were the 5 properties. Last properties, e raised to at into e raised to minus at, that is state transition matrix and its inverse. If you just find out and multiply them, you are going to get that multiplication is a identity matrix. So e raised to minus at always exists. If e raised to at exists, then e raised to minus at will always exist. E raised to at is a non-singular. What is meant by non-singular? Non-singular means determinant is not 0. Okay, so singular means determinant is 0. Determinant of that matrix is 0. Non-singular means determinant is not 0. So e raised to at is non-singular for all finite values of t. So these are the properties I have put together. So there is another slide with the properties you can find out. So this is written in a more structured fashion. So you can see here the first line also I have written as a property. So what is e raised to at? I have written that as my first property. So e raised to at is equal to I plus at plus 1 by 2 factorial a square t square plus 1 by 3 factorial a cube t cube and all, and that is equal to I is equal to 0 to infinity 1 by I factorial ai ti likewise. So I think I have made a very small mistake in the previous page while writing. So here this plus sign should be actually a equal to sign. Okay, because all this addition you are doing, and instead of plus sign there will be a equal to sign, and all this addition if you are doing, what you are going to get is e raised to at is equal to the thing that is shown here. So this kind of equation you are going to get. So please make this plus sign as a equal to sign that you do. So these are all about state transition matrix and properties of state transition matrix e raised to at. Now let us see some two big numericals and we will be over with this session. So still 20 minutes are there, so 10 minutes I will take for explaining. Now the same numericals, there is nothing different. Only thing is the dimension has increased. Okay, so this is the highest level of difficulty which can be asked for you to. So a is given in this case. So x dot t is equal to axt. You can remember that. So x dot t is equal to axt is a homogeneous system. That means but part is not there, so no forcing function is there. In that case, you will be asked to find what is the system solution. So what will be the system solution? E raised to at into x0. So first step I am finding what is e raised to at, and we have to multiply the initial condition with that. So x0, that means 3 values, 3 row 1 column, it will be given. Whatever e raised to at you find, you multiply x0 with that, and you are finding the solution for homogeneous system. So how to do that? That I will show you in the next numerical. Very easy thing. Once you find e raised to 80, just multiply one column with that, and that's it. But this numerical, we are going to see only how to find the state transition matrix for 3 by 3 A matrix. Okay, so A matrix is given a 3 by 3, you can see, but you can see there are 5 elements which are 0. So there is no need to get scared, because if all 9 elements are present, then it is little scary. But in this case, you are finding almost 5 elements are actually equal to 0. So what is the first step? First step is finding phi t. First step is find phi s. What is phi s? Si minus a. So this is Si for 3-dimensional. So how do I know it should be 3-dimensional? Because A matrix is 3 by 3. If in the previous numerical A matrix was 2 by 2, in that case Si we had taken 2 by 2, that is S00S. In this case, A matrix is 3-dimensional. Hence you are taking Si as 3 by 3 minus of A. So this is step is Si minus A we are doing. So Si minus A we have got like this. Okay, so what is Si minus A? Si minus A is actually a matrix, and whenever we are taking the inverse of Si minus A, that is actually is called as a phi s. What is phi s? Phi s is nothing but the state transition matrix in Laplace domain. And what is its use in Laplace domain? We are finding state transition matrix. If we are taking the inverse Laplace transform of phi s, we are getting phi t. What is phi t? E raised to at. It is called a state transition matrix required while finding the solution of any state variable differential equation. This is the significance. So without finding Si minus A inverse, or without finding phi t, we cannot go anywhere in state transition matrix. So this is a must step for all the numericals in state variable analysis. So how to find Si minus A inverse? So first step is to find a determinant. So this is what is shown here. So determinant, you are finding s cube minus 4s square plus 5s minus 2, which is nothing but s minus 1 whole square into s minus 2. Okay, so this is the determinant of Si minus A inverse. And we know this property, that is Si minus A determinant and Si minus A inverse determinant, they would be same. So here I am first finding Si minus A inverse determinant. So I found it to be 1 by s minus 1 whole square and s minus 2. Then what I'm supposed to find out is I'm supposed finding the matrix of cofactors and all these things. So this is how it is found out, and then adjoint cofactor, all those things you do. So this is actually Si minus A inverse. And then what you have to do is divide the denominator with that. So this s minus 1, s minus 3, s minus 1 square, s minus 2. That means numerator will be s minus 3, denominator will be s minus 1, s minus 2. This is what I have written. Here this is 0, so all the zeros will be 0. So in all A2 to A, all the even positions are 0 in this case, you have found out. Okay, and then this is minus 2 s minus 1, s minus 1 whole square, s minus 2. So this s minus 2 and s minus 1 and s minus 1 whole square, they get cancelled. So denominator only s minus 1, s minus 2 is there, numerator is minus 2. And see here I have written a this is called as a transpose. Okay, so if you take the transpose, then you are finding the actual Si minus A inverse. So I've taken the transpose here, that means this minus 2. Okay, so in this page, so after taking transpose only, I have found this. So previous stage it is transpose is taken. So in this step, transpose is already taken. So this minus 2 will remain here. Check here, this was minus 2 here. Okay, in the position of 3 1, but it has gone to 1 3 like this. Okay, so finally Si minus A inverse is this one. Okay, but this one you cannot find Si minus A inverse. Next step is you have to do partial fraction. So I have written here e raised to at. E raised to at is this is actually Si minus A inverse, and you take ILT. ILT stands for inverse Laplace transform. Okay, if you are taking here, before taking the inverse Laplace transform, you have to do the partial fraction, and you should be master in partial fraction to do good in this kind of mathematical subjects. Either you say control system or signals and systems, you should be master of partial fraction. And then I'm finding s minus 3 actually 2 by s minus 1 minus 1 by s minus 2 and all those things. Be very careful about the negative signs in all these cases. Finally, find what is the inverse Laplace of that. So it is s minus 1, then e raised to t it will be. So it will be 2 e raised to t. You are finding here 2 e raised to t. One more intermediate step I have done. And minus 1 by s minus 2. That means this will be e raised to plus 2t. Negative of that. So it is minus of e raised to plus 2t. Then the 0 will be 0. And then this is 2 by s minus 1. So this will be 2 e raised to t. You are finding it here 2 e raised to t. and minus 2 by s minus 2, this will be 2 e raised to plus 2t. So minus of 2 e raised to plus 2t. Then in the central position, there is only 1 by s minus 1. So it is e raised to plus t, and below the things are there. So now this is e raised to at. So what is e raised to at? There's a big equation, but only thing you are finding that all the four positions are zero. So only you have to find five elements. In this case, you are finding at 1 1, 1 3, 2 2, and 3 1 and 3 3. So these are the five positions where you are finding what are the elements, and all other element positions, they are going to be zero. So if all the nine elements are given in case of A matrix, then it is little scary. But for our case, A matrix was given and there were five zeros in that. Okay, so that's why finding this e raised to at was little easier. But all this transpose, cofactor, adjoint, determinant, all these things that you have learned, that you have to do. And one extra more thing is there that you have to do, what is called as partial fraction. So find Si minus A, then find Si minus A inverse, then find the partial fraction, and after finding partial fraction, find what is called as the inverse Laplace transform to get e raised to at or phi t, and it will be in the time domain. Now I am moving to solution of homogeneous system equation. Now, what is meant by homogeneous system? So, homogeneous system solution. So, this is one very important topic, and there will be another that is heterogeneous or non-homogeneous. We don't call it heterogeneous, but we call it non-homogeneous system solution. So, what is homogeneous system? X dot t is equal to axt. That is actually a homogeneous system. So, no forcing function is there. In that case, whatever e raised to at we have found, just multiply x0 with that. That will be the solution of homogeneous system, and x0 will be given to you. X0 is actually the initial condition of all the variables. If not given, you can assume, and you can assume absolutely anything. Generally, we assume 001, 010, 101, those kind of thing for the initial conditions. Okay, so just show that you know the step. You just, if x0 is not given, you assume any x0. So 101, 110, anything you assume, and just multiply e raised to at with x0. You are going to find the solution of the state variable analysis, state variable model in homogeneous form. So let us study that part, how to find the solution. So homogeneous system solution, that is the next topic. This is actually an application of state transition matrix. So external input is not given in state variable representation, because we know that x dot t is equal to axt plus but. In case of homogeneous system, ut is not given. That means we are not giving any external forcing function. So whatever response we are getting from the system, it is called its natural response or spontaneous response. In the third chapter, we have seen what is meant by natural response of RL circuit, RC circuit, and all. So we are not giving any external input. So we connected the external input, then we removed the external input, and we checked how the voltage or current is dropping in the circuit. So finding natural response is with the help of state transition matrix for homogeneous system. So homogeneous system is equal to x dot t is equal to axt. That's all. You have to stop there. So homogeneous system solution, external input is not given. That means ut is not there in the state variable representation. So system response is found only for its initial condition. This is called as zero input response. I'm sure you have done this zero input response and zero state response in case of signals and systems. So for any system given, if you are considering all the initial conditions, in that case, it will be giving you zero input response. And if you are considering only the external input, this is called as a zero state response. Okay, so we are trying to find here homogeneous solution, that is nothing but the zero input response, because we are considering only the initial conditions. So this is called zero input response, that is a homogeneous system solution. And this response is when no external input is connected to the system. That means ut is equal to 0. This ZIR stands for zero input response. This ZIR is responsible for the transient behavior of the system. So transient behavior is actually controlled by the input response, zero input, and steady state behavior or after transient behavior is controlled by the external input. So zero input response or transient response is actually controlled by the initial conditions. X0 is written here. X0 is the initial condition for all the system state variables. Here as there are three state variables. So this numerical I'm going to show you A matrix is equal to 3 cross 3. That means there are three state variables. That means x0 will be having dimension of 3 cross 1. That means 3 rows, 1 column. So x0 is always a column matrix, that you have to remember. Okay, A matrix and x0 matrix is only required to determine the homogeneous system solution in the state space. Let us see the numerical what is given. So x dot t is equal to axt, that is given. Okay, so but part is not there. So this is the state variable system representation for homogeneous system. X dot t is equal to axt, and x0 is given. X0 is the initial condition of the three state variables. So this xt is actually, if you write, it will become x1t, x2t, and x3t. What is x10? X10 is 1. That means that t is equal to 0. So you have not given any input. Initial first state variable is having amplitude as 1. Second state variable, that is x20, is having amplitude as 1. And third state variable x30 is having amplitude 0. So this x0 we require, A matrix we require. If we get these two, in that case we can find out what is called as homogeneous system solution for the given system. That means x dot t is equal to ax t. In that case, if we are giving x0 input, or if we know what is A matrix, we can find out what is called as the solution of this homogeneous system. So find solution of this system, find the state at time t is equal to 2 seconds. Okay, so after you find state transition matrix, multiply that with the initial condition, so you are getting the solution of this homogeneous system, and there you have to substitute t is equal to 2. So you are going to get x1t, x2t, x3t at t is equal to 2, some 3 values. That means what is the amplitude of the state variable x1 after time 2 seconds? What is the amplitude of state variable 2 and state variable 3 after time 2 seconds? All those things you can find out from x dot t is equal to axt and x0 if given. Okay, so let us find out first what is the state transition matrix. So A matrix is given -1 0 0 0 -2 0 4 5 -3. I'm sorry, this thing is little faint, but I think it is visible. Okay, so what is next? Find Si minus A. So Si is nothing but going to be a 3 by 3 matrix here, because A matrix is 3 by 3. So Si matrix will be also having 3 by 3. So now you are finding Si minus A. There is a matrix, and find delta. So delta is s plus 2, s plus 3. So you are finding s plus 1 into s plus 2, s plus 3 likewise, and that is it. Okay, so in that case you are finding this is s plus 1, s square plus 5, s plus 6. So this is actually s plus 1, s plus 2, s plus 3. That is actually delta. And next is adjoint cofactor and all those things you are finding. So Si minus A inverse is 1 upon delta, and then this is the thing and transpose of that. So what you are finding is Si minus A inverse, that is e raised to e raised to at, but in Laplace domain. That is equal to 1 by s plus 1, s plus 2, s plus 3, and this big one. This is also not a very big numerical, because you are finding that 4 terms in this are actually 0. Okay, so only you have to find partial fraction for the only 2 terms you are finding. So, okay, because the first term becomes 1 by s plus 1, because as numerator is s plus 2, s plus 3, denominator s plus 2, s plus 3 gets cancelled. So first term becomes 1 by s plus 1, second, third, fourth term is 0, sixth term is 0, fifth term. Okay, so here s plus 1, s plus 3 is there, that means 1 by s plus 2 only will prevail. And the last term diagonal 1 by s plus 3 will prevail. So out of 9 terms you have to find only 2 partial fraction. Just see. Okay, so only 2 partial fraction if you find, and you are through with it. So you have found 2 partial fractions, so and you are finding it to be like this. Okay, so this is actually now Si minus A inverse. Take the inverse Laplace of that, and whatever you are finding below, okay, this is actually called as the state transition matrix. So 1 by s plus 1, that means e raised to minus t. 1 by s plus 2, that is e raised to minus 2t. 2 by s plus 1, so 2 e raised to minus t minus 2 e raised to minus 3t. Likewise, 2 is taken outside. 5 is taken outside, so e raised to minus 2t minus e raised to minus 3t. Likewise. And the last term 1 by s plus 3, that is e raised to minus 3t. So whatever you are finding here, this is actually the state transition matrix e raised to at. So I told you that today's numerical we are going to find 3 state transition matrix. So first we have found the state transition matrix for 2 by 2 A matrix, and then we have found out state transition matrix for 3 by 3. So for 2 cases we have found state transition matrix for 3 by 3 case. That means A matrix is 3 by 3. How to find the state transition matrix? So up till here there is no problem. Now what we are trying to find is x dot t is equal to axt. A is given. We have found state transition matrix. Now final step. This is actually what we are doing, a solution of homogeneous system equation. So solution of the system x dot t is equal to axt, which is homogeneous system. Why homogeneous system? Because there is no but term. B chhod do. Main important thing is ut term is not there. So external forcing function, external input is not there. Whatever system response we obtain, that will be nothing but its transient response. That will be nothing but its zero input response. Why is it called zero input response? Because we are not connecting any external input. That's why the transient response is called as, or homogeneous system response is called as zero input response. So solution of the x dot t is equal to axt, which is a homogeneous system, is xt is equal to e raised to at into x0. So this, for the first time I'm showing you what is the formula for homogeneous system solution. So you can write it down and keep with you, or you can check this note when it is uploaded today. So what is a homogeneous system solution then? It is, the formula is xt. So xt will be a three-dimensional thing in this case. Okay, so 3 cross 1. That means x1t is equal to e raised to at into x10. X2t is equal to e raised to at into x20, and x3t will be e raised to at into x30. Okay, so all those things. So now xt is there, x1t, x2t, x3t, e raised to at is there, e raised to at into x0, because x0 in this numerical is given as 110. So whatever e raised to at you have found out here, write that and multiply 110 with that. So if you're doing that, so this is e raised to at matrix now. Okay, we have found whatever we have found, e raised to at, this is e raised to at multiplied by x0. So e raised to at into x0 is nothing but the solution of a homogeneous system. So if you're doing that, you're finding that this becomes a column matrix, okay, which is e raised to minus t, e raised to minus 2t, and 2 e raised to minus t plus 5 e raised to minus 2t minus 7 e raised to minus 3t. What is meant by that? It means that x1t is a exponentially decreasing state variable. I don't know what is x1, but I know what is the characteristic of x1. Okay, that is e raised to minus t, and x2t e raised to minus 2t. That means this is the faster falling thing, and we can find out that x2t variable is faster than x1. So x2 variable is more stable than x1, because x2t and x1t both are reducing. Okay, both are bibo kind of a response they are given, but x1t is falling in a flat way, in a slow manner, but x2t is falling in a faster manner. So area under the curve x2t, that is e raised to minus 2t, will be lesser. That means that x2t is consuming less energy. That means x2t will be more stable than x1. And what is x3t? So the last line of the e raised to at is complex. So if you multiply with 110, you are finding it. It is 2 e raised to minus t plus 5 e raised to minus 2t minus 7 e raised to minus 3t. So all three different dynamics are there in the third state variable. So x3 is the most complex state variable here we are finding, because there are three dynamics of exponential there. Okay, and final thing is, question was asked, find the state variable amplitude at time t is equal to 2 seconds. So first job is to find state variable. Second job is to find, multiply the initial condition with that. You are finding the solution of state variables, and then substitute whatever time is given. So I have asked you find the state variable amplitude at 2 seconds. So substitute e raised to minus 2. So e raised to minus 2 is 0.135. Here I also substitute 2. So you find e raised to minus 4. This is 0.0183. And last line also substitute t is equal to 2. You are going to find 0.3449. So this is actually how the state at any time is found for the given state variable. Okay, so now we have found out xt is equal to 0.135. That means this is x1t at t is equal to 2. That means this is x1 bracket 2. Below this is x2, that is second state variable at time 2. And last one is x3 bracket 2. That means x3 state variable at time 2. So this is the significance of e raised to at, and this is how e raised to at is used to find out the homogeneous system solution. For non-homogeneous system solution also, this step we have to do, e raised to at x0 plus there will be some other term. Okay, so for non-homogeneous system solution there will be two parts. One is the homogeneous system solution, e raised to x0 plus integration of e raised to at minus tau b u tau d tau. Okay, so an integration has to be done there into y2 matrix format. I will show you how to do those numerical. So for non-homogeneous system solution also, this first part, whatever we have done here, we will do. So non-homogeneous system is nothing but x dot t is equal to axt plus but. In their solution, xt e raised to at x0 will come plus integration of 0 to t e raised to at minus tau b u tau d tau will come. So next day, whenever the lecture is, we are going to see how to find the non-homogeneous system solution, and the first step in that also will be finding the state transition matrix. So today we are doing only this much. I have told you what is state transition matrix, the most important thing in finding the solution of state variable, which is required for finding solution for homogeneous as well as non-homogeneous system solution. So actually we are doing the solution of state variable analysis, and in that case first part is finding state transition matrix. I have told you what is state transition matrix. Tomorrow we will do solution of non-homogeneous system solution. Thank you. That's all from me today. Again, we'll meet tomorrow at 12:10.